Hello everyone, welcome to this previous year's question series on the subject of complex analysis. This is the very first question. So let us have a look at the question. This question is from December 2011 and it is of 3 marks. This question is from complex integration. So let us see what they are asking. They are saying if this integration is denoted by IR, right, where what is the CR? CR is given by this region. That means mod of Z minus 0 is equal to R. So that means this is a circle with center as 0 and radius as R, where R can have any value. So depending on which R can have any value greater than 0. So depending upon this value of R, we can have these 4 options. So let us see how to solve this question. First of all, here we have to see this region clearly. What is the region where we can integrate? And moreover, in that region, because here we are saying this is this CR, that is some curve with center, that is some curve, basically a circle with a center 0, and it could have some arbitrary radius R. So this is like this. So you can say a circle like this, right? So this is your CR, this point is somewhere R, and it could have any value. So here you have to check whether the given function 1 upon Z, Z minus 1, Z minus 2, this function, this is analytic in this given region or not. If it is analytic, then we clearly say by Cauchy's theorem that the integral IR is equal to 0. But here, can you see the points of difficulty? They are 0, 1 and 2, because if you substitute Z is equal to 0, you'll get this function as infinite, right? Similarly, when you substitute Z is equal to 1, you'll have Z as 1 upon 0, which is not defined, right? And when you have Z is equal to 2, the same problem is there. So we have 3 points where we cannot say the function is defined yet analytic, right? So what we do, we firstly apply the partial fraction to this function. So this is our function fz, 1 upon z, z minus 1, z minus 2. So we can apply a partial fraction onto it, and we can calculate the values of these 3 constants a, b and c. So the values of these 3 constants comes out to be like this. So we can write our function in this form, right? So now here we have to perform integration. So the region I have told you, this is the yellow portion, is our region where we have to perform the integration. So here we should note that Z is equal to 0 is a point of difficulty, Z is equal to 1 is a point of difficulty, and Z is equal to 2 is a point of difficulty, right? So you have to check here that if the point 0 or 1 or 2, they lie inside this region or outside this region. Say if your R is equal to 0.5, in that case only 0 lie inside this region, and if your R is equal to say 5, in that case your points 0, 1 and 2, they all lie inside your region. So in that case you cannot directly apply the Cauchy's theorem to calculate this integral, and we have to go and look for Cauchy's integral formula, right? So we have to apply that. So for that, what we do, we assume the case 1 where R is given to be some value within this open interval 2 to 3. So let us first understand what we are doing. So our R could vary among this interval 2 to 3. We are not including 2, we are not including 3. So that means, can you see these lines over here? So between these lines, the gray shaded portion, in the gray shaded portion, you can have any value of R. So I have assumed this arbitrary value over here. This is R. So between 2 and between 3, we have some value R over here. So I have assumed this yellow portion to be the CR for this case. and I've also assumed the direction of this curve to be anti-clockwise, so our orientation would be in the positive sense, right? So now in order to perform this integration over this region CR, what we have to check? We have to check, do the points z is equal to 0, 1 and 2, they lie into this region? Yes, we can clearly see that all these points 0, 1 and 2, they lie in the region. So this makes our region as multiply connected. So what we do here to convert this multiply connected region to simply connected region, we just we just create 3 circles circling the points 0, 1 and 2, having smaller radius such that they do not overlap each other, like in this manner, right? And we can join these 3 circles using 2 lines. Say I'm calling this first line as L1 and I'm calling the second line as L2. And I'm calling the first circle circling the 0 is C1 in the positive sense. Then with center 1, this is C2, and with center 3, this is C3. So basically C1 is Z is equal to some circle with with say epsilon 1. Epsilon 1 is sufficiently small. C2 is some circle with center 1 and some another radius, say epsilon 2, and C3 is some circle with center 2 and radius epsilon 3. So this is what I have assumed, and joining these are the lines L1 and L2. So basically what I have done, these are 3 circles and I have joined these circles through this lines L1 and L2. So when you move from this point, say from here, you have covered half of your circle C1, and then so half C1 here, and then here you have L1, this is L1, this is L2, and then half of the circle C2, and then L2, and then completed this third circle, so that means C3, and then you have minus L2 because you are traveling in this opposite direction of L2, and then we will cover this half circle, so that means it would be half C3 and then minus L1 and then half C1. This half C2, I guess. Yes, it is half C2. So you see this L1 and L1, this cancels, L2 and L2 cancels, and here half C1 and half C1 makes it to be only C1. Then half C2 and half C2 joins together to make C2, and then we have C3. So you saw how we have converted our region, this whole region. Say this was our region, right, including this point. So this whole region into this into the simply connected region. So this is our region now without any holes, right? So now we can perform the integration quite easily. So let us see how can we do that. For that, I have written the CR into this thing as I have just explained to you. Here L1 and these cancels with each other. So we are only left with the integration with respect over the closed circle C1, C2 and C3. So we have to perform this integration. Now in order to perform integration, let us see the case for the first circle C1. So in the first circle C1, this function 1 upon 2z, this is not defined because at z is equal to 0 we were having trouble. So for that, what we can do, we can apply this Cauchy's integral formula. It says if we have something of this form, so in our case we are to calculate this 1 upon 2 would come out, and we are to calculate 1 upon z dz over the region C1, right? So here we see that trouble is at point z0, so I'm taking z0 to be 0. So here basically our function f of z would be 1. This is 1, and so you see how we can calculate this value 1 upon, before that we just rewrite this formula like this. So it would be integration over C 1 upon Z minus Z naught dz, that would be equal to into f of z, right? So that would be equal to f at the point z naught multiplied by 2 pi iota. So this formula we'll be using. So now here our f of z in our case is simply 1. So f of z naught, f of 0 would be 1, right? F of 0 would be 1 because z naught here is 0. So this integration would be 1 into 2 pi iota. So this integration would be 1 into 2 pi iota. So let us substitute this value over here. So its integration would be 1 by 2 into 1 by 2 was outside into 2 pi iota. And then we have to perform the integration of these two terms. Now can you see these two terms, they are analytic with respect to the curve C1. Why? Because within this regions of C1, we do not have any problematic points. So that means we'll treat this whole these terms as analytic. So according to Cauchy's theorem, we say if any function is analytic in the simply connected domain D, now we have converted our domain D as simply connected, so their integration is 0. So the integration of these two terms would be 0. So it simply would be 0, right? So now let us calculate for C2. For C2, what we are saying, this function and this function, their integration with respect to C2 is 0. Why? Because they both are analytic. And now the problem here is by virtue of this function 1 upon z minus 1, because here in C2 was a circle with center at 1, right? So here this point 1 creates a problem. So that means we are looking for its integration according to Cauchy's integral formula would be f of 1 multiplied by 2 pi iota. And what was our f? F of z was simply 1 in our case, because here it is 1. So that is why we have this thing as equal to 2 pi iota. So this value is simply 2 pi iota with a negative sign. Why? Because here we have a negative sign, right? So this is for the second curve, and for the third curve, these two terms, they are analytic with respect to curve C3. So that means their integration would be 0. So we to perform the integration of this term with respect to C3 only. So that would be 1 by 2 as such, and again the integration over C3 of 1 upon z minus 2, this thing would be equal to f of 2 multiplied by 2 pi iota. Again f of z is 1 in this case, therefore this term is 1 into 2 pi iota, so it simply is 2 pi iota. So this term is this one. So when you calculate this, it comes out to be 0. And let us have a look at the options. So when r belongs to 2 to 3, they are given to be 2 pi iota. So this option is incorrect. Similarly, we can perform the integration for these three regions also. Let us have a quick look at these parts, right? When you guys practice this question, you can perform these calculations quite easily and quite rapidly, right? For the purpose of illustration, this in this video, this is taking long, right? For the second part, we have r in the region 0 to 1. So basically our r varies from 0 to 1. So our gray portion in we can have any value of r in this gray portion. So I have assumed this circle to be r. So for the current case, this yellow shaded portion is the given region, and this boundary could vary in this gray region. So accordingly, our CR in this region, the problematic point is only z is equal to 0. So we only have to create one circle. So say C1, that would be equal to z mod of z is equal to 1, is equal to epsilon, right? Where epsilon is very small quantity. So we have converted our CR to C1. See, this C1 CR is oriented in positive sense, and our circle is also, C1 is also oriented in positive sense, so no difference in sign. Here in this problem, in this integral, this term creates problem, and these two, they are analytic. Therefore, the integration of these last two terms give you 0 plus 0 plus 0, and here the integration would give you 1 by 2 as such, and the integration of 1 upon z, as I have explained previously, would be 2 pi iota. So it would come out to be pi iota. So the option number B here is pi iota, and they are saying it is 1 by 2. So this option is incorrect. So let us move on to third part. Third part says that our R is in the region, our R is in the region, just a second, 1 to 2. So in this gray portion, R could vary. So I have assumed R to be some random boundary, this one, right? So in the yellow portion, this is our domain. In our domain, you can clearly see that out of the points z is equal to 0, 1 and 2, we only have points z is equal to 0 and z is equal to 1 inside this region D, right? Inside this yellow region D. So what we do, we create two circles, C1 and C2, and we join them through a line L. This is line L, this is C1, and this second circle over here, that is C2. So we have converted again this region into simply connected region, again using this technique, right, like this. So whole of our circle, that has been converted to simply connected region. So here we can perform the integration with respect to C1 and C2, right? Again this L and minus L would cancel, covering this area. So we are only left with C1 and C2. So here the problematic point was this one. So it would be 1 by 2 into 2 pi iota. This by virtue of these two, because they are analytic, it is 0. And here these two are analytic, so it would be 0. And for this part, we have minus 2 pi iota. So overall it comes out to be minus pi upon iota. And in our option, it is not the same thing. Let us have a quick look. So this is given to be minus 2 pi iota, and we have evaluated it to be minus pi iota. And let us see for the last part. For last part, it should be equal to 0 when R is greater than 3. So let us have a look. When R is greater than 3, in that case, let us see the region. So that means R can take any value here after 3, right? So it could go anywhere. So I have assumed this to be R to be here. So basically this yellow portion is our domain, and here this is multiply connected because z is equal to 0, 1 and 2, they all lie inside this region. So here we have to convert this multiply connected region, in fact triply connected region, to simply connected region by creating 3 circles, say C1, C2, C3, and joining them by 2 lines, again by L1 and L2, so that our region CR now converts to C1 plus C2 plus C3. So here what we do, we just perform the integration firstly with respect to C1. So for C1, for this term, we have the quantity 1 by 2 into 2 pi iota. And for rest 2 terms, it would be simply be 0. So we only have this term. And according to C2, for this and this, because these are analytic inside C2, so it is 0. So for this quantity and inside this C2, we have minus 2 pi iota. And similarly for C3, for these first two, they are equal to 0. So for the last term, it is equal to 1 by 2 into 2 pi iota. So this is the term, and when you add up these two, we get 0. So that means option D comes out to be 0. The integration comes out to be 0. So option D is the correct option. I know this was a long video, but thank you for your patience and listening to this. Well, I'll see you in the next video.